Hi, I want to talk about the force of tension. And tension is a force that's experienced all through ropes, cords, cables, chains, any otherwise flexible object that is held straight with some force acting along the length of that object. Now, there is no simple way of calculating tension because tension, like some forces, is something that is as strong as it is, provided that the tension isn't damaging or destroying the cord that is experiencing that tension. And I'm going to use the word cord here to stand in for strings, ropes, chains, whatever. Now, the symbols we use for tension, I personally like a capital F with a subscript T for force of tension. A lot of textbooks will use a capital T with a little vector harpoon to describe force of tension. So regardless of the symbols you use, try and stay consistent. So for example, if I have a string that's connected to an object that then is connected to a second object sitting on a table and run over a pulley, all through that straight length of cord, there's going to be tension. And if I were to have, say, a pulley set up with masses on either side, which is also referred to as Atwood's machine, or if I just have, for example, a horse trying to pull a stone, and there's some sort of rope connected between the horse and the stone, that force all along that is the force of tension. So, in our class, we're going to make some assumptions about the cords that we use. And we're going to assume that the mass of the cord is negligible compared to the mass of the objects on either end of that cord. Now, sometimes that can be a really good assumption. On the other hand, if you're dealing with a steel boat chain, then that could be a very, very bad assumption. We're also going to assume that the length of the cords while under tension doesn't change. And that assumption, again, is something that can be very good, but it can also be incredibly bad. So we're basically going to say if a string or cord or cable stretches, then once it's stretched, that stretch will remain constant as long as there is some tension along the cable. So, tension then is experienced undiminished all along the length of that cord. And the reason why it's undiminished is because if the mass of the cord is zero, then it takes no net force to accelerate that cord as a system containing that cord is accelerating. So if that horse is supplying sufficient net force to start accelerating the stone, then the net force acting on that cord between the horse and the stone would be zero. So whatever horse the force feels pulling backward towards the stone would be exactly the same force that the stone feels being pulled towards the horse. So you can think of an ideal cord and ideal tension as being like a Newton's third law machine, where we take a look at the end of that string and our force is going to act directly along the direction of the string as it leaves our object. And at either end of that string or that cord, we would have the same force, but since the ends of the strings are going away from each object in opposite directions, that force would be going in opposite directions. And that force remains constant until that string makes contact with an object. So, for example, here in these first two examples, I have a pulley. Now, that cord is making contact with the pulley here and the pulley there in my second picture, and it's making contact with my pulley here and my pulley there in the first picture. Now, it is possible for there to be a tension in this length that is different than the tension in that length. And in the real world, that is absolutely the case. But for the first several chapters, until we get into talking about rotational motion and rotational inertia, we'll assume that the tension remains constant all along the entirety of that rope. Thanks for watching.